Now next topic is cosets and Lagrange's theorem. Let G be a group and H be any subset of G. Then the set AH, HA are defined as AH is equals to AH such that H belongs to H. A is an element from G. Also, let A belongs to G. A is an element from group G and H is an element from subgroup H. HA, this is equal to HA such that H belongs to H. Next, now what do you understand by cosets? Let H be a subgroup of a group G. Let A be an element of group G. Then the set AH, this is equal to AH such that H belongs to capital H. Means whenever in this AH the element from the group is applied from the left side, then it is called as left coset. This is called the left coset of H and G. Containing A, HA, this is equal to HA such that H belongs to H. Now here the element of the group is applied from the right side, so it is called the right coset of H and G containing A. Now example, let G is equals to S3, symmetric group with 3 symbols. So its elements are identity, 1 2, 1 3 cycle, 2 3 cycle, 1 2 3 cycle, 1 3 2 cycle. Now let H is equals to identity 1 2 3, 1 3 2. Let us pick one element from this group G. Let A is equals to 1 2. This belongs to group G. Now left coset. This is AH such that H belongs to H. So this means A will be multiplied to every element of this H. AI, comma, A into 1 2 3, A into 1 3 2. And what is A? A is 1 2. So 1 2 into identity, 1 2 into 1 2 3, 1 2 into 1 3 2. So this is equal to 1 2 cycle. Can you tell me what will be this after doing their product? and this also.
One three.
1 3 for which one?
First one. 1 2 and 1 2 3.
No.
Three से one.
1 goes to 2.
अच्छा ठीक है, आप रिवर्स कर दो. Just a
2 goes
minute.
to 1.
3 से 1 1 से 2. ठीक है.
Then 2
से
goes
3.
to 3, 3 goes to 3. So 2,
ठीक.
3.
1 2 1.
And what will be this? This last one?
Just a 1 2 3. 2. All three.
Yes, 1 3. Now write coset HA such that H belongs to H. So identity into A, 1 2 3 into 1 2, 1 3 2 into 1 2. So this is equal to 1 2 only. And what will be this? Calculate both these.
First one is 1 3.
Yes.
Second one is 2 3.
Yes. Now some results and observations. First, cosets are usually not subgroups. For example, if I take the previous example only, where G was S3, H was identity 1 2 3, 1 3 2. Element A was 1 2, AH. This is equal to 1 2, 2 3, 1 3. So this is a coset, but this is not a subgroup. Can you tell me why?
as when we make the operation, then
Operation
1 to 3 and 1 3 2 का करेंगे, that will not belong to H, no? That's why it's not subgroup.
कौन से एलिमेंट्स?
अगर मैं 1 2 and 1 2 3 करूँ क्या आएगा इससे?
1 2 and 1 2 3
नहीं 2 3 से फर्स्ट 2 तो इससे क्या आएगा?
1 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 3, 3 goes to 2, 2 goes to 1, 1 2 3. This does not belongs to AH. So closure property fails. ये तो कैलकुलेट करके करना पड़ा, बिना कैलकुलेट करे सिर्फ देख के भी तो बता सकते थे. आइडेंटिटी नहीं है ना, आइडेंटिटी नहीं है सिंपल इसमें. सब ग्रुप या ग्रुप होने के लिए उसके पास आइडेंटिटी होनी ज़रूरी है. नेक्स्ट, इफ H इज अ सब ग्रुप ऑफ G, AH is a subgroup of G if and only if A belongs to H. So here this A was from group G. This A was not from subgroup H. If A is from subgroup H, then only I can say that AH is a subgroup of G. Is this clear? Next, A belongs to AH where H is a subgroup of G. Simple reason for this, we know that identity belongs to H because H is a subgroup of G, so it has identity. Therefore I can write A as A into A. This is equal to A, so this belongs to AH. Next, let group G is equals to Z9 and H is equals to 0 3 6. Now let us consider the following cosets. Now in case of symmetric groups, the operation was basically composition of two cycles. Now here it is Z9, so what will be the operation? Addition. So 0 plus H, so this will be 0 3 6. Next, 3 plus H, this will be again 0 3 6, because you will add 3 in this, then you will get 3 6 and 9. Sorry, it is addition modulo 9, and we will see the remainders only. So 3 6 0. Then 9 plus H, it will be 9 12 15. Again addition modulo 9, we will see the remainders only 0 3 and then 6. So AH is equals to H if and only if A belongs to H. This is absorption property. Here I have picked this A from this subgroup H only. That's why I am getting AH as H only. Here also A plus H is H, A plus H is H, A plus H is H. Reason is because I have picked this A from this subgroup H. Next, two cosets are either equal or disjoint. Means either two cosets are equal or they are disjoint. For A not equal to B. For example, if I take group G as Z9, which contains 0, 1, 2, 3, 4, 5, 6, 7, 8, and subgroup H as 0, 3, 6. We have already seen that 0 plus H is equals to 3 plus H is equals to 6 plus H. Now I want to find 1 plus H. So it will be 1, 4, 7. So this will be 7 plus H. Also it will be equal to 4 plus H, because if I calculate 4 plus H, then it is 4, 7, 10 and addition modulo 9. So remainders will be 4, 7, 1. 2 plus H, this is equal to 2, 5, 8, and addition modulo 9, it will remain same only. And if I calculate, basically I am finding the missing ones. I have already calculated 0 plus H, 3 plus H, 6 plus H. Now I have calculated 1 plus H, 2 plus H, 4 plus H, 7 plus H. Now next is, if I calculate 5 plus H and 8 plus H, these two are left. So 5, 8, 11, and addition modulo 9 will be 5, 8, 2. 8 plus H, 8, 11, 14. Addition modulo 9, 8, 2, 5. So I can clearly see that 2 plus H is equals to 5 plus H. This is equal to 8 plus H. So basically 0 plus H is equals to 3 plus H is equals to 6 plus H, and 1 plus H is equals to 4 plus H, and this one 2 plus H is equals to 5 plus H is equals to 8 plus H. So we can clearly see that two cosets are either equal or disjoint. I can see that 2 plus H intersection with 7 plus H. This is 147, this is 258. Clearly they are disjoint. Next, order of every coset is equal. That is, order of AH is equals to order of BH. Means if there are two different cosets, then their order are equal. Next, define AH A inverse is equals to AH A inverse such that H belongs to H. Now, left coset is equals to right coset if and only if AH A inverse is equals to H. And in general, left coset is not equal to right coset. For example, let Group G is equals to S3, H is equals to 1, 2, identity. Now, if I take element A as 1, 3 from group G, then I will calculate 1, 3H left coset and then right coset. 1, 3, 1, 2, 1, 3 into identity. Can you tell me what will be this? Second one is obviously 1, 3 only.
One, two, three. First one.
Yes, 1, 2, 3. And this one?
One, three.
This is 1, 3. 1, 2 into 1, 3.
Achha, 1, 2 into 1, 3. So 1, 2 से 2 से 1. अच्छा, okay. Set B. Sorry, 2, 3.
नहीं.
Correct.
Here 1 goes to 3.
Just 1, 2 है ना? 1, 2, 1, 3, 3. One, two, three.
नहीं. अब देखो, जब भी हमें दो साइकिल्स का प्रोडक्ट निकालना है ना, एक सिंगल साइकिल में उसे लिखना है, तो राइट साइड से स्टार्ट करो. यहाँ पे चेक करो, 1 goes to 3. फर्स्ट साइकिल में 3 कहाँ पे जा रहा है? 3 पे ही जा रहा है ना, लिखा नहीं है इसका मतलब 3 पे ही जा रहा है. सो यहाँ पे मैंने 3 लिख दिया. अब 3 यहाँ पे राइट साइड में कहाँ पे जा रहा है? 1 पे जा रहा है. लेफ्ट साइड में
अच्छा,
1
मैंने ना
कहाँ पे जा
बोलने
रहा
में गलती कर दी. ठीक है सर, गॉट इट. 1, 3 और 2 आएगा.
So clearly left coset is not equal to right coset. 1, 3H is not equal to H, 1, 3. Next, AH is equals to BH if and only if A inverse B belongs to H. A small proof for this, AH is equals to BH, so I can pre-multiply by A inverse. Please mute yourself. So A inverse AH, this is equal to A inverse BH. So this will become identity. So H is equals to A inverse BH. Now by property second, it was that AH is equals to H, then A belongs to H by second property. ये वाली AH is equals to H if and only if A belongs to H. So A inverse B belongs to H. Next is Lagrange's theorem and its corollaries. Theorem. Let G be a finite group and H be a subgroup of G, then order of subgroup divides order of G. Moreover, the number of distinct left cosets of H in G is order of G upon order of H. This is equal to index of G is to H. Now some corollaries. Let G be a finite group and A belongs to group G, then order of A means order of element divides order of group G. This is possible only when G is a finite group. Second, a group of prime order is cyclic. Third, let G be a finite group and A belongs to group G, then A to the power order of G is equals to identity. Again, this is possible only when G is a finite group, because if G is an infinite group, then its order will be infinite and A to the power infinite will never be identity. Next is index of a subgroup. Let G be a group and H be a subgroup of G the number of distinct left cosets of H in G is called the index of H. So, index of any subgroup is the number of distinct left cosets of H in G. If G is finite and H is a subgroup of G, then the index of H in G is given by order of G upon order of H. This is equal to index of G is to H. And this can be written only when G is of finite order. Now some remarks. The converse of Lagrange's theorem is not true in general. That is, if G is a finite group, then it is not necessary that corresponding to every positive divisor of order of G there exists a subgroup of G. Converse of Lagrange's theorem is not true in general. That is, if G is a finite group, then it is not necessary that corresponding to every positive divisor of order of G, there exists a subgroup of G. Example. This example is very important. A4, the alternating group on the set one, two, three, 4 is of order 12 because order of an alternating group is n factorial by 2. So order of A4 will be 4 factorial by 2, 24 by 2, 12. It has no subgroup of order 6. Now, order 6 is possible if it is a 6 cycle or if it is a 3 cycle and 2 cycle, because order of a 3 cycle into a 2 cycle is simply their LCM, na? LCM of 3 and 2, this is 6. Only these two possibilities are there. 6 cycle is not possible because this alternating group A4 has only 4 symbols, 1, 2, 3, 4. 6 cycle is not possible. And then 3 cycle into 2 cycle, this will also be not possible. Let me prove it by contradiction. Let it possible suppose that H is a subgroup of A4 such that order of H is 6. Now S4, in S4 how many elements of order 3 are there? This was the formula, na? To find number of elements of order 3 simply means number of cycles of order 3 which have length 3. So this will be 4 factorial upon 3, 4 minus 3 factorial. So 24 by 3, 8 na? Is this clear? This formula I have discussed na? क्लियर हुआ ये 8 कैसे निकला?
Yes.
That is 3 cycle and all of them belongs to A4. Let A belongs to A4 such that order of A is equals to 3. This be arbitrary. So index of A4 is to H. Order of A4 upon order of H. Order of A4 is 12. Order of H is 6. So this is 2. Then the cosets of H in A4 containing A must be H, AH, A square H, as index of A4 is to H. This is 2. Therefore, at most 2 of them should be equal. So, possibilities will be 3. Either H is equals to AH, or AH is equals to A square H, or A square H is equals to H. So if H is equals to AH, then I have that property na, AH is equals to H if and only if A belongs to H, absorption property. So this means that A belongs to H. Now here I can multiply by A on both sides. Its reason is because I have picked this A as an element of order 3, and definition of order says that A to the power 3 is equals to identity. So A square H is equals to A cube H. A cube is identity, so this is H. So A square H is equals to H. AH is equals to A square H. A square H is equals to AH. So by combining these two, I will get AH is equals to H. Again, absorption property, A belongs to H. Now last, here also I can multiply by A. Multiplying by A, I will get A cube H is equals to AH. A cube is identity. EH is equals to AH. So AH is equals to H. Again, A belongs to H. Thus, in every case, A belongs to H. Now as A was arbitrary, therefore every element of order 3 is in H. Every element of order 3 is in H, but order of H is 6. This is a contradiction. So, the converse of Lagrange's theorem holds in case of abelian groups. Means if G is any finite abelian group, and D is any positive divisor of order of G, then there exists a subgroup H in G such that order of H is equals to D. Next is Cauchy's theorem. Let G be a finite group and P be any prime dividing the order of the group that is P divides order of group. Then G has an element of order P. Next, some extra results on Lagrange's theorem. First, let order of G is equals to PQ, where P and Q are prime. Then every proper subgroup of G is cyclic. Second, UN, where n is greater than 2, is of even order. Let G be a group and H be a subgroup of G then AH is equals to BH if and only if HA inverse is equals to HB inverse. Now let us practice some previous year questions. PYQ. First question is on class equation. This is a very important topic. Which of the following equations can occur as the class equation of a group of order 10? A part, 10 is equals to 1 plus 1 plus 1 plus 2 plus 5. B part, 10 is equals to 1 plus 2 plus 3 plus 4. C part, 10 is equals to 1 plus 1 so on till 1 10 times. Okay, ये वाला क्वेश्चन मैं आपको सॉल्व करवाती हूँ, फिर मैं ट्राई करने के लिए दूंगी क्लास इक्वेशन कैसे करते हैं, क्योंकि मैंने बताया नहीं है ना कैसे करते हैं ये वाले टाइप के क्वेश्चन.
हाँ जी, मैं भी वही कहना चाह रही थी, अभी तक करवाया नहीं क्लासिफिकेशन।
क्लास इक्वेशन वैसे थोड़ा सा टॉपिक बता दिया था, बट क्वेश्चन कैसे करना है इस फॉर्म वाले वो रह गया था बताना। सो सबसे पहली बात, जब भी आपको ये कुछ भी 10 इक्वल टू समथिंग करके दिया हुआ है, सो हेयर these one will denote the order of center. So in A part we can observe that order of center of G is 3. 1 plus 1 plus 1, 3. Here order of center of G is 1. Here it is 10 only. So first thing, order of center will divide order of group G. In A part I can clearly see that order of center of G is 3, which does not divide 10. So option A is clearly discarded. Now in B part, one more thing you need to observe, that whichever order is given in this class equation, it will definitely divide the order of group G. Again I can see that this 3 does not divide 10. 3 does not divide 10. Basically, these are the order of conjugacy class of G. Here 3 is an order of a conjugacy class of G, and order of conjugacy class is equals to order of group G divided by order of normalizer. So it must divide order of group G. So option B is also discarded. In option C, this can be the class equation of which group Z10. Class equation of Z10 is 10 is equals to 1 plus 1, so on till 1. So answer will be option C. मतलब ना आप इसको सिंपली ऐसे देखो, और एग्जांपल्स करते हैं इसमें पहले, फिर और प्रीवियस ईयर डिस्कस कर लेंगे। जैसे मैं, मतलब सिंपल लॉजिक है, S3 की मैंने क्लास इक्वेशन लिखनी है, ठीक है। पहले ये बताओ मुझे S3 में कौन कौन से ऑर्डर वाले पॉसिबल हैं एलिमेंट्स। 3 सिंपल्स हैं, 1 2 3। इसके एलिमेंट्स लिख ही लेते हैं। आइडेंटिटी 1 2 1 3 2 3 1 2 3 and 1 3 2. So clearly order 1 element is possible, order 2 elements are possible, and order 3 elements are possible. So basically class equation of this S3, order of S3 is 3 factorial, which is 6. So 6 को हमने क्या लिखना है, कितने एलिमेंट्स ऑर्डर 1 के, कितने एलिमेंट्स ऑर्डर 2 के, कितने एलिमेंट्स ऑर्डर 3 के। सिंपली यही है हमारी क्लास इक्वेशन। सो यहाँ पे क्या बन जाएगा, ये 1 प्लस 3 एलिमेंट्स ऑफ ऑर्डर 2 एंड 2 एलिमेंट्स ऑफ ऑर्डर 3। क्लियर हुआ कैसे लिखते हैं?
यस मैम।
S4 की क्लास इक्वेशन लिख के दिखाओगे? S4 means order of S4 is 4 factorial. अब 24 एलिमेंट्स लिखने काफ़ी टफ है, तो जो मैंने फॉर्मूला सिखाया है ना उनका यूज़ करना।
उसके अंदर तो ऐसे आएगा फिर एक तो आइडेंटिटी मैट्रिक्स होगी, दूसरा
मैट्रिक्स नहीं साइकिल,
सॉरी आइडेंटिटी होगी, हाँ साइकिल। एक होगा 6 होंगे 2 ऑर्डर्स के, फिर
नंबर
4
ऑफ
होंगे,
साइकिल्स ऑफ ऑर्डर 2,
6 होंगे वो।
ऑर्डर 2 वाला
6 होंगे ना, 1 2 1 3 1 4 2 3 2 4 3 4।
अच्छा देखो, ये भी ध्यान रखो, जब भी ये कैलकुलेट करते हो ना साइकिल्स, जैसे ऑर्डर 2 की करनी है, हेयर आई हैव 4 सिंबल्स, तो ऑर्डर 2 लिख रही हूँ तो 1 2 लिखना है, तो साथ में ये 3 4 जो नहीं आ रहे हैं वो भी लिखना है। साइकिल में आई मीन जितने भी सिंबल्स हैं ना इस S4 में, वो कंप्लीट करते हुए जाना है। तो इस टाइप की तो फॉर्मूला मैंने बताया था कैसे निकालते हैं।
पर 1 2 का मतलब ये नहीं है कि 1 से 2 2 से 1 3 का 3 4 का 4।
वही है।
अच्छा, तो इसको ऐसे लिखना जरूरी है? 1 2 में नहीं इंक्लूड हो जाएगा वो? 1 2 में नहीं?
फिर वो फॉर्मूला डिफरेंट हो जाता ना, जो मैंने 2 टू द पावर लेंथ इनटू एन आई फैक्टोरियल ऐसे करके एक फॉर्मूला बताया था।
अच्छा,
वो फॉर्मूला फिर डिफरेंट अप्लाई हो जाएगा ना, इसीलिए।
नहीं तो अगर हम इसको ऐसे भी लिखते हैं तब भी तो 6 ही एलिमेंट्स आएंगे ना इस टाइप के। हैं?
हम्म, 6 ही है।
ये एनसीआर नहीं होता? जैसे आपने लिखा एन फैक्टोरियल अपॉन आर इंटू आर एन माइनस आर फैक्टोरियल, तो ये आर फैक्टोरियल नहीं होता?
ये वाला एक सेकंड में देखती हूँ। NCR नहीं NPR होता है।
NPR होगा, फिर तो आर भी नहीं आएगा, फिर तो एन फैक्टोरियल अपॉन
NPR अपॉन R ये होता है।
अच्छा,
नंबर ऑफ साइकिल्स ऑफ ऑर्डर 3 कितने आए थे?
ऑर्डर 3 के तो फिर 8 आएंगे।
ऑर्डर 3 के करेक्ट। ऑर्डर 2 हो सकता है, ऑर्डर 3 हो सकता है, आइडेंटिटी हो सकता है, इस टाइप के हो सकते हैं 1 2 3 4।
एक ऑर्डर 4 भी हो सकता है।
हाँ तो ये वाला ऑर्डर 4 ही हुआ ना, LCM ऑफ 2 and 2 4।
तो जो ऑर्डर 4 के होंगे वो होंगे 6,
ऑर्डर 4 एक सेकेंड। यस, ऑर्डर 4 वाले मतलब आप सिंपल कह रहे हो ना, 1 2 3 4 ऐसा साइकिल, इस टाइप वाला साइकिल ना।
हाँ
नंबर ऑफ साइकिल्स ऑफ ऑर्डर 4। अब देखो ऑर्डर 4 वाले में दो टाइप के हो गए ना, एक तो ये ए बी सी डी इस टाइप का साइकिल, या ए बी सी डी इस टाइप का साइकिल। सो दिस इज इक्वल टू 4 फैक्टोरियल अपॉन 4 इंटू 4 माइनस 4 फैक्टोरियल, सो दिस इज 6 एंड दिस विल बी, इसका वो वाला फॉर्मूला जो मैंने एक और बताया था, दिस विल बी 4 फैक्टोरियल अपॉन 2 to the power 2 इंटू 2 फैक्टोरियल। ये क्लियर हुआ ये वाला फॉर्मूला?
हाँ हाँ याद आ गया।
ठीक है, सो 24/8 3, तो 9 हो गए ना। ऐड करके दोनों को, नंबर ऑफ साइकिल्स ऑफ 4 ऑर्डर 9, 1 2 3 4 8 9। सो देखो अब चेक कर लो, S4 विल हैव वन एलिमेंट ऑफ ऑर्डर 1 आइडेंटिटी 1 प्लस 6 7 प्लस 8 15 प्लस 9 24 हो गए। तो क्लास इक्वेशन विल बी 1 प्लस 6 प्लस 8
प्लस 6 प्लस 3
प्लस 6 प्लस 3। सो इस तरीके से क्लास इक्वेशन लिखी जाती है।
इंक्रीजिंग ऑर्डर में लिखना होता है इसको, क्लासिफिकेशन में तो कोई ऐसे लिख सकते हैं।
नहीं, हमने वैसे ही किया ना, देखो ये ऑर्डर 1 वाला, ये ऑर्डर 2 वाला, ये ऑर्डर 3 वाला,
ऑर्डर 4
फिर ऑर्डर 4 वाला में दो टाइप की पॉसिबिलिटीज थी, या तो 2 साइकिल या अकेला 4 साइकिल, तो अकॉर्डिंगली हमने लिख दिया।
अच्छा, इसमें जरूरी नहीं है कि ये इंक्रीजिंग या असेंडिंग डिसेंडिंग ऑर्डर में लिखे जाए,
बस ऑर्डर इंक्रीजिंग ऑर्डर में जाए। ऐसे नहीं कि मैंने पहले 4 ऑर्डर वाला लिख दिया, पहले 1 से ही लिखा जाएगा, 1 प्लस समथिंग, क्योंकि मैंने इस SN के लिए भी बताया था कि ऑर्डर ऑफ सेंटर ऑफ दिस SN इज इक्वल्स टू आइडेंटिटी, इसीलिए 1 से स्टार्ट किया जाता है हमेशा। ठीक है, सिमिलरली होमवर्क है S5 का ट्राई करना, ध्यान से ट्राई करना है इसका, ठीक है, और मुझे नेक्स्ट क्लास में बताना कि क्या आएगा, क्योंकि इंपॉर्टेंट है। ऑप्शंस में दे देते हैं और पूछ लेते हैं कि कौन सी क्लास इक्वेशन है कौन सी नहीं है, और इसका
एक क्वेश्चन तो आता ही है क्लास इक्वेशन का।
हाँ, हर बार एक्सपेक्ट कर सकते हैं इस टाइप का क्वेश्चन, और आसान है, बस एक बार ध्यान से करना है। नेक्स्ट, determine which of the following cannot be the class equation of a group. A part, 10 is equals to 1 plus 1 plus 1 plus 2 plus 5, and this is MSQ, more than one option can be correct. Part C. B part, 4 is equals to 1 plus 1 plus 2. C part, 8 is equals to 1 plus 1 plus 3 plus 3. D part, 6 is equals to 1 plus 2 plus 3.
ए एंड ए तो है ही है, ए एंड सी.
What about B?
B 1 plus 1 to center of the group order 2 और 2 से डिवाइड होगा. नेक्स्ट 2.
B पार्ट में थोड़ा और ध्यान से सोचो.
और एलिमेंट्स का कौन सा ग्रुप होगा?
B part, order of center of G is 2.
2 तो डिवाइड कर रहे हैं ना 4, वो तो हो ही रहा है. बाकी ये जो 2 है
Order
next वाला.
of, एक सेकेंड, order of G by ZG is 4 by 2.
2.
Every group of prime order is
साइक्लिक.
prime implies cyclic and cyclic implies
abelian.
abelian. ZG is already abelian, so this means that G is equals to ZG, means order of G by ZG is 1, which is a contradiction ना.
2 आ रहा है.
तो B डिस्कार्ड हुआ ना. I mean B टिक किया जाएगा क्योंकि नॉट ट्रू पूछा है. और A पार्ट में ऑर्डर ऑफ सेंटर
D3 आ रहा है. 10 does not divide 3.
does not divide 10. So A is also correct. In C part also 3 does not divide 8. And what about D? D part?
D तो अभी किया है ना S3 का 6.
Yes. D is wrong because this is class equation of S3. So answer is option A, B, C.
C is also not true, no?
C भी true नहीं है. Next, let S9 be the group of all permutations on the set 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the total number of elements in S9 that commutes with tau is equals to 1, 2, 3, 4, 5, 6, 7 in S9 equals now how to approach these type of questions. We are given a cycle and we are asked that total number of elements in S9 that commutes with this tau. Okay. So basically I need to find order of normalizer of this tau because normalizer commutes with elements of this group S9. So its formula is same formula, order of class of tau. This was order of group G divided by order of normalizer of tau. So simply order of normalizer tau will be order of group G divided by order of class of tau. Okay. Now firstly I will calculate order of group G. It is simply 9 factorial. Order of class of tau means I need to compute order of class of 1, 2, 3, 4, 5, 6, 7. So this will be 9 factorial upon, there is one cycle of length 3, so 3 to the power 1 into one cycle of length 4, 4 to the power 1, and I have told you that you need to complete this 9 symbols because S9 is given. So 8 and 9 will be like this. So 2 cycles of length 1. So 2 to the power, 1 to the power 2 into 1 factorial into 1 factorial into 2 factorial. So finally order of n tau, this is equal to 9 factorial divided by 9 factorial upon 3 into 4 into 2. So this is 24. So whenever you will be asked that how many elements commute with a particular cycle, then you need to apply this approach. Now next, let G be a group of order 231. The number of elements of order 11 in G is so firstly order of group G is 231. Do its prime factorization, 3 into 7 into 11. And here I have asked that number of elements of order 11. So firstly I will find the number of subgroups of order 11. So I will find this by using Solo's third theorem. N11, this is equal to 1 plus 11k, which divides 21. So k can be only 0, only this possibility will be there. This means that N11 is equals to 1. That is, there exists a unique cyclic subgroup of order 11. Because we know that every group of prime order is cyclic, that's why I have written that there exists a unique, because I am getting N11, this value as 1, cyclic subgroup of order 11. Now number of elements in a cyclic subgroup of order 11 is computed by using Euler phi function, phi 11. We have studied this formula, na? Phi p is equals to p minus 1. P to the power n, एक सेकेंड, 5p, अगर 5p निकालना है तो p to the power n minus p to the power n minus 1, ऐसा कुछ था.
नहीं वो तो जब होते हैं जब सिर्फ पावर होती है, अब ये तो सिंपल पी हो ना।
तो 5p equal to p minus 1. 10. So this is the answer.